Hiya, DT Mr. C here, and this is the second video on mechanical devices.
In the last film, he showed us what mechanical devices really were and taught us about the 4 types of motion. We learnt all about the 3 different classes of lever, and he gave us practical examples of which was which. Just when you thought it was safe, he's back to teach us about linkages, the bell crank, crank slider mechanisms, and cams and followers.
In my first film on mechanical devices, we looked at levers, and when you connect levers together, you make linkages. Lots and lots of machines have them. There's lots of different types. We're going to look at the most common ones.
This mechanism consists of 3 linkages. It's pivoted together in 2 places with moving pivots, and it's fixed in the middle with a fixed pivot. The input is pushed, the output goes the opposite direction, and that's why it's called a reverse motion linkage. And here's an actual example that I've built out of MDF. As you can see, the 2 white pivots are the moving pivots, and the metal screw in the middle is a fixed pivot. So you push the input, the output goes in the opposite direction, and vice versa. By changing the position of the fixed pivot, you can actually change the amount of force at the output, and you can also change how far the output moves compared to the input. On this example, the fixed pivot's closer to the output. This means it doesn't move as far as the input, but there's more force. You'll notice that my finger and thumb are guiding the output linkage. This is just to make sure it moves in the right direction. Right, so this next mechanism consists of 5 linkages. There's 2 fixed pivots and 4 moving pivots. The input and the output both go in the same direction, but the link arm at the bottom travels in the opposite direction to the input and the output. This is called a push-pull linkage or a parallel motion linkage. And here's an example of one that I've built from MDF. The white pivots are the moving pivots, and the metal screws in the middle are the fixed pivots. The reason I'm holding the output linkage is just to keep it going in the right direction. We're going to look at cranks now. Now basically a crank is a lever that's attached to a shaft, and if you rotate the crank, the shaft also rotates. And this is how bikes work. You've got a pedal connected to a crank, and your foot pushes the crank round, transmitting power to the back wheel via the chain. And the metal rod that I'm touching there is the crank.
The crank is a really useful mechanism. You don't just find it on bikes. Here we've got a crank slider mechanism, so you rotate the crank like that, and the slider moves up and down, so it changes rotary motion of the crank into reciprocating motion of the slider. That's called a connecting rod that connects the crank to the slider. These 2 things at the side are guides, otherwise the slider would move from side to side. And we've also got 2 moving pivots there and a fixed pivot there.
I've seen this mechanism used in a machine where the crank is attached to a motor, and it just keeps running and running and running to test the fabric for wear.
And this mechanism is used in most car engines as well. What you get is a mixture of fuel and air at the top. That explodes, it pushes the piston down, and that in turn causes the crank to rotate, and the crank, through the gearbox, is connected to the wheels and causes the wheels to rotate. Another mechanism here that uses a crank, you've got the crank there, you've got a connecting rod here, you've got this linkage here that's fixed to the board at that end. When you turn the crank round, you get that kind of motion, which is what's used in quite a lot of windscreen wipers.
And because it's a complicated mechanism, I had to model it in Lego first. This is something you should consider doing in your projects.
Right, so the bell crank mechanism consists of an input, the bell crank itself, and an output. It's got 1 fixed pivot there, 2 moving pivots there, and if you push the input and pull the input, the output moves at 90 degrees to it. The reason it's at 90 degrees is because the input's in that direction, the output is in that direction, which is at 90 degrees to it. I also wanted to show you a version of the bell crank mechanism that's commonly used in bicycle brakes. It's this part here. When you pull it, you can see that the input of pulling the brake cable is vertical like that,
whereas the output is moving at 90 degrees to it in that direction. It's exactly the same principle as this. It's a bell crank. It's just that the actual crank itself is a different shape. The first cam we looked at is called the eccentric cam, and I wanted to draw that for you so that you understood what it was. What eccentric means in this sense is something that's circular, but the shaft isn't quite in the centre. So when you've got the follower on top of it, it will rotate off centre and push the follower up and down. So imagine it rotating. I'll draw it again in a different position. Obviously the shaft stays where it is at that same level there, but this time it's rotated round through 180 degrees and the follower now is lower. So as I say, that's called an eccentric cam. It means circular and off centre. Right, I just want to show you 3 more followers that are different to the ones on the model that I showed you earlier. So the first one's called a flat follower, and as the name suggests, it's got a flat bottom there. These are quite good because they're quite hard wearing and they last quite a long time, but they're not particularly accurate, and I'll come on to accuracy in a minute. So that's called a flat follower. This second one is called a knife follower or a point. And imagine a cam that's not just round, it's quite a complicated shape. It might be something that controls the operation of a machine. So it might have all these curly bits on it and stuff. The main advantage of the knife or point follower is that it's accurate because it's got a very, very sharp point. It will be able to follow all of these contours on the cam. Right, so that's accurate. And you can see now, can't you, why the flat follower isn't that accurate. Okay, on the downside, because it's got a sharp point, it wears out quickly because you've got moving parts. You've got a very small part there where it goes to a point, and obviously that's going to wear out. The third one is called a roller follower, and it actually has a wheel attached to the bottom. And again, these are accurate because the roller part of it at the bottom has got a relatively small surface area. So roller follower. And because it's on a wheel, its action is really, really smooth. It doesn't stick or jam or anything like that. So on the plus side, it's smooth and accurate. Sorry. On the negative side is because it's got moving parts, you see. These moving parts may wear after time, but also it's going to be more expensive to produce because of the moving parts. Okay, so that's different followers. Right, I'd like you to have a go at making some of the mechanisms that you've seen in this video. You don't need anything fancy. A bit of corrugated card. It works better because it's thicker than regular card. Some of these paper fasteners, split pins, you can see those, or something to pivot them together. Maybe a bit of glue, scissors. Be careful when you're making holes and that you don't use something too sharp. And this is obviously the bell crank. In year 10s, with your NEAs coming up soon, you'll be wanting to get good at making models and then testing them, evaluating them, improving them, and going around in that iterative process that the exam boards want you to do.
Doesn't necessarily have to be projects that have got mechanisms in either. You need to model things anyway.
Right, well, I hope you've enjoyed Mechanisms. I've been DT Mr. C, and I'll catch you soon. Bye.
I need you more than oxygen.